Hi everyone, let's get started on 16.2 or continue in 16.2 and let's look at the del operator. So f is a real valued function of f of x, y, z. So actually I should have put that earlier. So suppose f is a function of x, y, z. So it's a real valued function, meaning the output is real. And the del operator basically does the partials of those. So that's equal to, and it's a vector, right? So they end up getting a vector. Okay, there we go. Which would look like this. So the vector, you do the partial f with respect to x, and then you do the partial f with respect to y, and then the partial f with respect to z. And that's ijk form, so it's a vector. So you can consider like the del operator like an operation, like a multiplication table or a division table or division or something. Symbol is what I'm trying to say. So it could look something like this. You can say partial with respect to x, partial respect to y, and partial respect to z. And then when you do, if you treat this like a dot product, then you end up doing this operation. Okay, so using that del dot f is equal to this, then again, that is like a vector valued function once you do that. So once you calculate del f, then you get a vector valued function or like a vector field. That's what you end up getting. So here's the definition of, so I got to be careful here. This isn't dot, this is just del f. So del f is defined to be that, which is a vector field. Okay, let's define next conservative vector field. So definition of what's called a conservative vector field. And this basically would be like fields that have conservation of energy, is one way to think of it. So conservation of energy idea, it would be like gravity fields, magnetic fields, those kind of fields, electrical fields. I can't think of any off the top of my head, but those are the type that we're looking at. So what it says is a vector field capital F is conservative if there exists a little f such that del f is equal to capital F. And little f is differentiable yes, that's period. Okay. So if that little f exists, then f is called the potential function. So little f is called a potential function for capital F. Okay, so we will look at a simple case first that we can just basically guess. right, so let capital F of x, y, so we'll just stay in 2D, equal to 2x comma 4y. So this is like your m and this is n. So it'd be 2xi plus 4yj, and we are in 2 dimensions right now. And then can we guess what partials of a function would give us 2x? So you're thinking derivatives with respect to x. And so what function do you know whose derivative is 2x? And you're really just doing the antiderivative, right? I mean, you're going backwards. So if you go backwards, you get x squared for the first one. And the second one is close, but you need a 2 in front. So it's 2y squared. So if you do the partial of f with respect to x, you get 2x. With respect to y, you get 4y, because the other terms end up being 0. All right, so you can check that. So you can show the partial f with respect to x. That is clearly 2x, which is the first value of this right here. No, here. All right, and then let's fit in here. So partial f with respect to y is 4y, which again is this one. And then of course that's 0. Okay, so there, that's your 4y. All right, so let's continue. We won't have to guess. We're going to develop a method to do that. Let's do tests for conservative vector fields in 2D. So if a vector field is conservative, then it has a lot of other properties that we can establish. So this is test for conservative vector fields. In 2D. We'll do 3D later, but for now we'll stick in 2D. So let m and n have continuous first partials on an open, on an open region R. Does not include its boundary points. F of xy equal to mn, or let's write that as mi plus nj, so that's just in 2D, is conservative The definition means that the potential function exists. This is the test to determine if that potential function exists. So is conservative if and only if partial n with respect to x, remember it's mn, so in respect to x equals partial m with respect to y. Okay, so if that's true, then a potential function exists. And we can check above on this one. So n with respect to x is 0, and m with respect to x is 0. So the top one does work. So you could check this one above if you wanted to. So little test. So we do partial n with respect to x. Well, n is 4y, so that's just 0. And does that equal partial m with respect to y? And m with respect to y, well, it's 2x, so it's partial 0. So that's true. So that works out, of course. Okay. Let's take a look at this. Let's see. All right, so we define work. Let's look at this example. Okay, so example. So we're going back on this to just evaluate along a curve. So this is an I hadn't done enough examples of just line integrals. So let's evaluate this line integral along a given curve and calculate what that is. Okay, so evaluate. We will do more on conservative vector fields a little bit later. So evaluate the line integral over C of 2xy dx plus x squared plus y squared dy along, now you got to define your C. So, before it was, when you integrated over a region in 3D, or you integrated on from A to B on the x-axis, right? Or effectively your t-axis, whatever, horizontal axis. So now we're looking at evaluating or integrating over a curve, right? So before we had a region, now it's a curve in 3D, or it could be 2D, but that's what we're looking at. And then later we'll look at integrating over a surface, okay, and then integrating over a volume, right? So those are the progressions we will look at. Okay, so along C, so what is this? Along the circular arc C given by x equals cosine t, y equals sine t. And this is for t in or between 0 and pi halves. So we can calculate what that arc is, but we don't necessarily need it. So going back to our calculation formula, we want to take a look at this. So if that's our x is cosine t and our y is sine t, then if you calculate your dx, that equals minus sine t dt. Let me move that over. And your dy is equal to cosine t dt. So when we integrate and substitute for everything, we get this. So we'll just do this one. Substitute for your x and your y and your dx. So what we get is integral over c 2xy dx. So we're doing one at a time, right? And so you get, it's the integral from 0 to pi halves, 2 cosine t sine t, and then dx is negative sine t dt. And then we can simplify that a little bit. That is negative 2 times integral from 0 to pi halves. And then you'll have the sine squared t cosine t dt. If you pick u to be sine t, then du is minus cosine t dt. And so you're just integrating and you end up getting the 1/3 and substitute. So I'm speeding this up a little bit. You may want to spend more time on it, but you get 2/3 sine cubed t, and you're evaluating that from 0 to pi halves. Sine of 0 is 0, and then sine of pi halves is 1, so you get just negative 2/3. Okay, and then now let's integrate over c of x squared plus y squared dy. And that's the integral from 0 to pi halves. And so what is x squared plus y squared if x is cosine and y is sine? Okay, that's Pythagorean identity, and you get just 1. So it's really just dy. So dy is cosine t dt. And now you're just integrating that. So antiderivative of cosine is sine, and you get just sine of t evaluated from 0 to pi halves. And then sine of pi halves is 1 minus 0, so it's just 1. So then you just add those up. It's negative 2/3 plus 1, which is 3/3, so it's just 1/3. Okay, so this is just another example that I wanted to add of integrating a line integral over a curve. This is in rectangular, and then you're converting to parametric. So that's pretty much what you need to do each time. Okay, a couple more things. So let's go ahead and define. No, let's go ahead and stop there.